After going through this module, you should be able to explain the classical theory of the Raman effect and polarizability, explain the quantum theory of the Raman effect and understand the rotational Raman spectra. So, as for all the other topics, we first begin with the classical theory of the Raman effect and try to understand Raman effect from the classical point of view. Then we see what is the effect of the quantum theory, and then we talk about the rotational Raman spectroscopy. Raman spectroscopy is another form of spectroscopy which is used for structure determination. Unlike the other techniques, it is based on the scattering of light. When a beam of monochromatic radiation passes through a liquid or gas, it might be transmitted, absorbed or scattered. In the case of light scattering, nearly all the scattered light is observed at the same frequency as the incident radiation. This phenomenon is known as elastic or Rayleigh scattering. However, the great Indian physicist Sir C.V. Raman observed in 1928 that some of the scattered light also has discrete frequencies above and below the incident frequency. Raman spectroscopy is based on the scattering of light, and what we observe is that most of the light that is scattered is of the same frequency as the incident radiation, and this phenomenon is known as elastic or Rayleigh scattering. But then Raman also observed certain other frequencies which were either above or below the incident frequency, and this phenomenon came to be known as inelastic scattering or Raman scattering. The Raman effect comprises a very small fraction, about 1 in 10 raised power of 7 of the incident photons. A powerful laser source in the visible or UV region is used as the light source, and this effect is much smaller than the Rayleigh scattering. So, you need very sophisticated instruments and you need a very high incident radiation from a laser, and this is usually in the visible or UV region. Now, this phenomenon is shown in what is Rayleigh scattering and what is Raman scattering. The lines at lower frequency than the incident radiation are known as Stokes lines, and those which are at higher frequencies are called anti-Stokes lines. So, you see in this figure that in the middle you have a molecule that absorbs radiation, goes up to a virtual level and then comes down to the same level with the same frequency, obviously because it comes back to the same level, the frequency is the same, and this is what is Rayleigh scattering. On the other hand, if it goes to a virtual level and then comes down to a level which is higher than the previous level from which it had gone up, then the energy of the radiation is decreased, and this is called the Stokes effect. The molecule absorbs some of the energy of the radiation, and the same thing happens in the case of anti-Stokes radiations. It is the molecule is already in an excited state, it goes to a virtual state by absorbing the radiation, and then it comes down to the ground level and giving some energy to the radiation which is now at a higher frequency, and this is known as anti-Stokes lines. Here we have plotted the frequencies and not the wavelengths. Now, you will see there is a difference between this and the other techniques that you have studied up till now. The first thing is that up till now we were saying that only those radiations will be absorbed which follow Bohr's law that delta E should be equal to h nu. It should be the difference in energies of two energy levels. Now, it can be a higher energy radiation that is absorbed, and then the molecule is either absorbing the radiation, part of the radiation, or it is emitting some energy to the radiation. So, unlike the other techniques, the molecular property that must change for a rotation or vibration to be Raman active is not the dipole moment that you have been seeing up till now, but this is molecular polarizability. And what is this molecular polarizability? You might have learnt in your inorganic chemistry. The polarizability is the ability, it is the ease with which the electron cloud in a molecule can be distorted. This rule should be contrasted with that for IR and microwave activity, which states that the molecular rotation must produce a change in the electric dipole moment of the molecule. Thus, Raman spectroscopy can be used on species with no dipole moment, for example hydrogen, chlorine, any homonuclear diatomic molecule. And the reason is that these molecules, although they do not have a permanent dipole moment, they can still be polarizable, and that means that whatever information you could not get from microwave spectroscopy, you can get from Raman spectroscopy. So, it is a complementary kind of technique to microwave spectroscopy. So, as usual, we begin with the classical theory and we talk about what is this molecular polarizability that we talked about. When a static field is applied on a molecule, a polarization of charge takes place. The positively charged nuclei will get attracted to the negative pole of this field, and the electronic cloud, which is negatively charged, it will try to go towards the positive pole. That means even if the molecule did not have a dipole moment initially, there will be what is called an induced dipole moment. A dipole is induced in the molecule even if it has no dipole moment initially, and the molecule is said to be polarized. It is not symmetrical any longer, it is now polarized. The induced electric dipole moment, we will be denoting it as mu induced, depends on both the magnitude of the applied field E, and this is a vector quantity, and the ease with which the electron cloud of the molecule can be distorted. So, I can say that mu induced is proportional to E, or you can say mu induced is equal to alpha into E, where alpha is the polarizability of the molecule. We will denote the polarizability by a term alpha. Now, this polarizability is anisotropic. It is not isotropic. What does it mean? That all directions are not the same, that the induced dipole moment also will not be the same in all the directions. Suppose we are talking about a linear diatomic molecule, the polarizability is greater along the bond axis than across it, since it is difficult to polarize in a direction perpendicular to the internuclear axis. Now, since it is anisotropic, we conveniently represent it by drawing what is called a polarizability ellipsoid. The ellipsoid is a three-dimensional surface whose distance from the electrical center of the molecule is proportional to 1 by square root of alpha I, where alpha I is the polarizability along the line joining point I on the ellipsoid with the electrical center. Thus, where the polarizability is greatest, the axis of the ellipsoid is least, it is the minor axis of the ellipsoid. So, what we do is we find the electric center of the molecule the point at which the dipole moment is balanced, and then we draw different lines in different directions, and these lines we are denoting by I. Measure the polarizability along this direction, and on both sides you plot a point at a distance of 1 by square root of alpha. The surface that you obtain is an ellipsoid, and since you are plotting with respect to 1 by square root of alpha, if alpha is large, the point will be closer to the electric center. That means we will be talking about the minor axis of the ellipsoid, and where alpha is greatest, in that case it will be the minor axis, and where alpha is smallest, it will be the major axis. Now, since the polarizability of a diatomic molecule is the same in all directions at right angles to the bond axis, along the bond axis it is the maximum, but anywhere on right angles to the bond axis it is the same. The ellipsoid therefore has a circular cross section in this direction, and in this we have shown the hydrogen molecule, which could be any homonuclear diatomic molecule. This is what we have drawn, that suppose you place the molecule like this, and in all these directions the polarizability across the bond axis, perpendicular to the bond axis, it is small. So, there you have the major axis of the ellipsoid. For convenience, we have drawn a two-dimensional figure, but actually this is a three-dimensional figure, and then along the bond axis the polarizability is maximum, because you can distort the molecule most along the bond axis, and so you have the minor axis of the polarizability ellipsoid here. This is just to illustrate what we are talking about. Actually, it is a 3D figure. When a sample of diatomic molecules is subjected to a beam of radiation of frequency nu, the electric field experienced by each molecule varies as follows. That means that the instantaneous value at a particular time is given by E, which is E naught, the amplitude, sine 2 pi nu t, you know that it is a sine function, and that means that since the electric field is varying as a sine curve, the time dependent dipole moment is also varying as a sine curve, and what you can say is mu induced is equal to alpha E, which can also be written as alpha E naught sine 2 pi nu t, and E naught is the strength of the applied field, actually the amplitude that we discussed about initially. So, according to electromagnetic theory, an oscillating dipole emits radiation whose frequency is the same as its oscillation frequency. So, there is a dipole moment which is oscillating with a frequency, and what is this frequency? It is the same frequency as that of the applied field. So, according to electromagnetic theory, the classical theory, if you have an oscillating dipole moment, it will start emitting frequency which is of the same as that of the oscillation frequency, and you can now see that this explains Rayleigh scattering very well, because it says that the frequency of the emitted radiation will be the same as that of the absorbed radiation. Now, if in addition the molecule undergoes some internal motion, which could be a vibration or a rotation, which changes the polarizability periodically, then the oscillating dipole will have superimposed upon the vibrational or rotational oscillation. So, not only is your E naught varying, E varying, but what also is varying, the polarizability is also varying, because you have an oscillating dipole moment because of the polarizability also varying due to some molecular property such as rotation or vibration that is happening simultaneously in the molecule. So, the oscillating dipole moment has frequency then nu of the incident radiation plus or minus nu vibration. That means, if it gains energy, it will be nu vibration. If it loses energy, then it is, if the molecule absorbs radiation, the radiation loses some energy, and so the frequency of the emitted radiation will be lower, and if the molecule is emitting some energy, this will be absorbed by the radiation and the radiation will be at a higher frequency. So, it should be noted that if the vibration or rotation does not change the polarizability of the molecule, the dipole oscillates only at the frequency of the incident radiation, you observe only Rayleigh scattering. But if the polarizability changes during the vibration or rotation, in that case this much energy will either be gained by the radiation or it will be lost by the radiation. So, we have a selection rule for Raman spectroscopy. In order to be Raman active, a molecular motion or vibration, rotation or vibration, must cause some change in a component of the molecular polarizability. A change in polarizability is reflected by a change in either the magnitude or direction of the polarizability ellipsoid. We have seen that the polarizability is represented as an ellipsoid. What do we mean by a change in polarizability? Either the magnitude changes, that means it becomes smaller or larger, the polarizability ellipsoid, or it changes its direction. So, this was the classical theory. Now, we come to the quantum theory of the Raman effect. According to the quantum theory, radiation of frequency nu can be pictured as a stream of particles called photons, each having an energy which is given as h nu. These photons are imagined to undergo either inelastic or elastic collisions with molecules. Inelastic collisions result in energy exchange between the photon and the molecule, while elastic collisions result in no energy exchange at all. So, if the molecule gains energy delta E from the photon will be scattered with an energy h nu minus delta E, because it has given delta E to the molecule, and its frequency then will be nu minus delta E by h. If, however, the molecule loses energy delta E to the incident radiation, the scattered radiation will have a frequency of nu plus delta E by h. Radiation scattered with a frequency lower than that of the incident radiation is known as Stokes radiation, while that of a higher frequency as anti-Stokes, it is called as anti-Stokes radiation. Rayleigh scattering is a situation where the scattered radiation has the same frequency as the incident radiation, and we have seen that most of it is Rayleigh scattering. So, we come to the first kind of spectroscopy, and that is pure rotational Raman spectra, and we restrict ourselves to linear molecules. It is easier to begin with linear molecules, or diatomic molecules is even simpler. From figure, it is clear that the polarizability ellipsoid of a diatomic molecule changes in appearance when the molecule rotates, because it will be either rotating perpendicular to the bond axis, and it will be continuously changing its polarizability ellipsoid. And for the first time, we are able to get rotational constants for homonuclear diatomic molecules like H2 and N2. Up till now, whatever kind of spectroscopy we talked about microwave spectroscopy. There the selection rule was that the dipole moment should change during the rotation, which means that the molecule should have a permanent dipole moment. So, all these molecules, hydrogen, nitrogen, oxygen, any one of these homonuclear diatomic molecules, you could not study its microwave spectra. When we went to the vibrational spectroscopy, the infrared spectroscopy, the selection rule was that the dipole moment must change during the vibration. Now, for a diatomic molecule, the only kind of vibration that is possible is stretching motion, and because during the stretching the dipole moment does not change, it remains 0 throughout, these molecules were IR inactive also. That means we were not able to observe either their pure vibrational spectra or even their rotation vibration spectra, and we were not able to determine their rotational constants. But we find that these molecules are polarizable, and that means we will be able to study their Raman spectra. But symmetrical molecules like CCl4 and SF6, which had 0 dipole moment and they were microwave inactive because their ellipsoids are spherical, they are neither microwave active nor Raman active, since the polarizability ellipsoids neither change size nor shape during rotations. So, we are able to determine the rotational constants of diatomic homonuclear molecules, but still for symmetrical molecules which had spherical moment of inertia ellipsoids, they have spherical symmetry. So, their polarizability is also isotropic, it is the same in all the directions, and when they rotate it does not change shape, and that is why these molecules are also Raman inactive for rotation. It is also clear from figure that the polarizability ellipsoid of a linear molecule presents the same appearance twice during a complete rotation. So, once you rotate by 180 degrees, it looks the same, and then again for a 360 degrees rotation it looks the same. A rotation it is looking the same. The selection rule for rotational transition for Raman spectroscopy is delta J should be equal to either 0 or plus minus 2. The delta J is equal to 0 selection rule refers to Rayleigh transitions, because nothing changes, the molecule does not absorb any radiation, and delta J is equal to 2 to emissions and minus 2 to emissions, and we may ignore both of these in case of absorption. Since we are talking about absorption spectroscopy and we are talking about Stokes lines, we will look only at the delta J is equal to plus 2 selection rule. The rotational energy levels of linear molecules are given by Fj is equal to B bar j into j plus 1, we already know, and j can take on values, any integer value 0, 1, 2. Here we have not considered centrifugal distortion, since accuracy of Raman spectroscopy is not too high to warrant its inclusion. You have already seen that it is much smaller than B, and so we can ignore it when you are studying Raman spectroscopy, and we will do that. The energy difference between the excited and ground state is given by delta E is equal to Fj plus 2 minus Fj, and we substitute all the values, B bar into j plus 2 into j plus 2 plus 1 minus B bar j into j plus 1, and this gives us B bar into 4j plus 6, and j is the rotational quantum number of the lower state, and it can take on values 0, 1, 2. The lines resulting from these energy changes are referred to as the S branch line, since we have considered only delta J is equal to plus 2. So, if the molecule gains rotational energy from the photon during oscillation, we have a series of S branch lines on the low wave number side of the exciting line, which are called the Stokes line, while if the molecule loses energy to the photon, the S branch lines appear at the high wave number side, and these are called anti-Stokes lines. The wave numbers of the corresponding spectral lines are thus given by nu is equal to nu 0 plus minus b bar into 4j plus 6, where the minus refers to the Stokes lines because they are at the lower wave number side, and the plus to the anti-Stokes lines. The allowed transitions and the Raman spectra are shown in figure. The spacing between adjacent lines is 4 b bar, and the first line on each side of the exciting line is at 6 b bar. Thus, the Raman spectra yields values of b bar, and hence you can determine the moment of inertia, and from there you can find out the bond lengths for small molecules. And you can see that Raman spectroscopy is complementary to microwave and infrared methods. It is a method for obtaining molecular parameters of homonuclear diatomic molecules, which are IR and microwave inactive due to the absence of permanent dipole moments in these molecules. And you have this spectra. You can see that the first line that is observed is from 0 to j is equal to 2, which has an energy difference of 6 b bar. Then the other one is from j is equal to 1 level to the third level, and here the energy difference is 10 b bar, and so on. The next one is j is equal to 2 to 4, and here the energy difference is 20 minus 6 is 14 b bar. So, you have the first line at 6 b bar, then after that the spacing is 4 b bar for every subsequent line. Similarly, on the higher energy side also the same thing happens, and you have the pure rotational Raman transitions and the spectrum. We will understand this using an example. The wave number of the incident radiation is 20,000 centimeter inverse. What is the wave number of the scattered Stokes radiation for the j is equal to 0 to 2 transition in nitrogen? The equilibrium bond length is given as 110 picometer. So, for a homonuclear diatomic molecule, we have already seen that the reduced mass is given by the atomic number, the atomic mass 14.0067 into 10 raised to the power of minus 3 to make it in from grams to kg, divide by 2, because the reduced mass of a homonuclear diatomic is half the mass, and you divide by Avogadro's number, and what you get is a value which is 1.16293 into 10 raised to the power of minus 28 kg. The moment of inertia is given as mu r square, and you substitute the value of mu, and r square has also been given. You can find out the rotational constant also, which turns out to be, using the same formula, b bar is equal to h by 8 pi square IC, and you find that the value turns out to be 1.985 centimeter inverse. The Stokes lines occur toward the low wave number side, and the first transition is at 6 b bar. Therefore, the line will appear at 6 into 1.985 subtracted from 20,000, and this gives you 19,988 centimeter inverse. So, this is how you can get the rotational constants of diatomic molecules using rotational Raman spectroscopy. So, finally, a brief summary of this module is given. Raman spectroscopy is based on the scattering of light. Most of the scattered radiation has the same frequency as the incident radiation, and this is called Rayleigh scattering. A small part has discrete frequencies at the lower that is Stokes lines and higher anti-Stokes sides. For a species to be Raman active, the vibration or rotation must cause some change in the polarizability of the molecule. A change in polarizability is reflected by a change in either the magnitude or the direction of the polarizability ellipsoid. Raman spectroscopy can give information about species with no dipole moments, hence it complements microwave and IR spectroscopy.